Okay, so welcome back. And the last time we left off with the question of what is a fluid, right? This is where we were last time. And I told you that the answer to that is a little bit more complicated. The book tries to give you a very simplistic answer to this question as to what exactly is a fluid, but we'll take a slightly more roundabout manner, and I think it's a more enriching understand. It will give you a little bit more enriching understanding of or enriched understanding of what a fluid is. So when we had said what is a fluid, we had also said basically anything that flows is a fluid, right? What does that mean? Well, if you go back to again to your book, what they do is they'll take this example where they have a parallel plate, and then this region is full of some fluid, and then you apply some stress on the top wall, and then the question is whether this starts to flow also or not. And the book says, and there are different books uh, which will all try to approach what is a fluid from this perspective, and then they will say that something of the order of that anything that flows under an applied shear is a fluid. But here there is a very important thing that is missing, and the discussion of the observer is missing. So the question is, who is observing this motion, and what is the time scale associated with this kind of an observation? So this T observation, let's say, what is this? What is this time scale? What kind of a watch is he using or she using? Or, if it's an alien being, what kind of a watch are the alien beings using? Because for us, maybe a few seconds is a good enough time frame, but for an alien creature, it might be that creature might be able to watch things at 10 to the power minus 15 seconds. If that thing is observing a fluid motion at 10 to the minus 15 seconds, do you really think there will be appreciable motion in that time? Or maybe it's an alien being like Kumbhakarna who's sleeping half the time and is watching it every 6 months. In that case, even something as difficult as butter or jam will have flown down. So maybe he's making one observation, Kumbhakarna is making an observation once every 6 months or once every many years. So this question of time scale of the observer is not usually addressed in many textbooks, and that makes the question of what is a fluid a little bit ill posed, because everything we typically understand in the context of an observer and how that observer is looking at the thing. So I'm going to take a little bit of a historical detour here, and it will feel as if the historical detour has nothing to do with this question of what is a fluid. But I assure you, when I'm finished, we'll come back to this question, and it will help you understand what that question is, or what the answer to that question is, rather. Okay, so having said that, let's just go into this historical detour. And before I go to the next slide, basically what I'm going to discuss are, so I'll just take a historical detour and discuss natural time scales. And natural time scale, especially in the context of the Indic sciences. Now, there are many civilizations which came up with different time scales to observe different or quantify different uh, phenomena, but perhaps some of the most beautiful time scales discussed amongst all the different ancient textbooks is in the Indic textbooks, where there are so many different time scales that have been associated with the natural events. For example, there is a time scale called Nimesha, which is associated with the duration taken for the twinkling. And here it's a twinkling of a star. Okay. So you can understand it's a fraction of a second. In some textbooks, the Nimesha is associated with the blinking of an eye, but end of result is the same. It's basically a small part of a second. There were even smaller time scales have been discussed in the text, and for example, Truti is another time scale, and this Truti is defined as the time taken by a sharp needle in piercing a lotus leaf. So if you are an archer shooting an arrow, and then what is the time it takes for this arrow to pierce through a lotus leaf, lotus petal, that is Truti. And you can guess, even if you don't know the exact value of what this should be, you can probably guess that this will be a very, very small value, much less than a second. Obviously, there are other natural time scales, for example, days, lunar months, year. So all these different time scales were there, and the reason this is important and interesting is because you can see that these time scales are defined in terms of some natural events. So the observer, so if you are an observer who wants to observe the twinkling of a star, for example, the natural time scale for your observation is the Nimesha. If instead you are watching something very fast, for example, that piercing of a lotus petal, then the natural time scale for you is a Truti. For an observer that is watching maybe the universe, the natural time scale, there are some other time scales like Manvantara and the Mahayugas and all, and those are massively large time scales. So maybe in case of that kind of an observer, those are the right time scales to take. So these are very, very beautiful time scales that were present, that were discussed in some of our older, very ancient texts. By the way, this discussion that I'm doing is I've taken some, I've borrowed from this particular book, Ancient Indian Leaps into Mathematics, and this has been edited by Yadav and Mohan. They are not the main authors. It's a compilation of many essays by many very accomplished authors. So if you are interested, you can take a look at this book. Now, these time scales were not just discussed in an abstract fashion, but they were given very, very unique distinctions. So, for example, again, this goes back to the same book. So, for example, we have 15 twinklings or the 15 nimesha, which makes one kashtha, and then we have 30 kashthas, which make one kala. And this, by the way, this minute is not our minute exactly. And then you have 30 minutes, which make up 1 hour, which is a muhurtam. And finally, you have 30 hours, which make up a day. And we know that the ancient Indians were very good at timekeeping because their understanding of what of an year was very precise. So we know that all these calculations are that these conversions are correct because there are conversions for the year are given. And here it also says that this one muhurta is 48 minutes of the modern time, so almost a current hour. Again, the basic idea of why we are discussing these natural time scales is because we want to have an appreciation of the fact that there are different phenomena which need which need observer with different kind of watches, and your watch has to be in sync with the event that you want to understand or the event you want to study. So we have these different time scales that are there, and we know that the delineation of these time scales rather well, because these small time scales can be built up to create days, weeks, etc., years, and the rest of the year was known, as I said earlier also. So I hope this is just a historical detour, but here what we are trying to establish is the relevance of the observer and the kind of a watch that that observer has. So the observer is wearing a watch, and this watch and the demarcations on this watch are very important to us, because this will tell us how we are doing the experiment, how are we going to observe flow. This brings us to a very interesting experiment which I want to tell you about, and again this emphasizes the relevance of the observer. So this experiment is a very famous one. It's called the pitch drop experiment, and this is by the way, this is a manuscript taken from European Journal of Physics, 1984. You can probably just do a quick Google search and get this. It's a very famous experiment, the pitch drop experiment. There is a YouTube video as well which explains the historical I think it's a 10 to 15 minute YouTube video, explains the entire history of the pitch drop experiment. You might be interested, and if you are, you can just look it up. But the experimental setup is shown here, right here. Okay, so what you have is, you have this cone which is filled with pitch. And you know what pitch is. We use this to make our roads, right? It's thick, solid, basic object. So this is placed in this glass funnel, and then the bottom of this funnel was cut. And this, I think it was set up, so okay, it says here itself, it was set up in 1927 by Professor Thomas Purnell. Okay, he was a professor of physics. And the pitch was basically warmed and poured into a glass funnel with the bottom of with the bottom of the stem sealed, and then after some time this bottom was cut. Once this bottom was cut, this liquid here, or rather the solid pitch, can now flow down under the action of gravity, and it can you see this pendant drop? This is the pendant drop. And this pendant drop is going to fall into this jar over here. So this is a jar right here, and it's just going to fall. Okay, let's just for a second do a thought experiment. Forget the pitch. If we just put water, okay, and if we make this tube thin enough, you expect small droplets to come out. You've probably seen this, right? From your faucets, leaky faucets, you'll have this drop coming out irritatingly at a very periodic, in a periodic manner, right? And so we know that if we keep liquid in a jar, the liquid is just going to form these droplets and come out. If it was water, it would come out rather quickly, and you could just sit there and observe many droplets fall if you are sitting there for about few minutes. But in the case of this pitch, which is actually a solid under most cases, actually this is solid in this particular case, in the traditional sense of the solid, this drop forms and drops down into this puddle, but it takes a very long time. And if you don't know about this experiment yet, before I turn to the next page, I just want you to take a wild guess how long do you think it would have taken? A week, few weeks, month, year? Okay, well, okay, I'll get you the answer. See, the record of the pitch drops right here. The first one, the stem was cut in 1930. Then the first drop falls in 1938. There's a gap of 8 years. Then 1947 and 1954. It's almost 8-9 years gap for every drop to fall. So imagine you are an observer with a watch where the 1 second in that watch corresponds to 10 years. What would you observe? What you'd see is a pendant drop falling every second in your watch, right? Much like you would do if you were watching water fall out of a leaky faucet. So interestingly, you can look at, and I encourage you to go back and read this paper if you can. It's a very by the way, chapter 1 is not going to be part of the exam. This is just to get you started. Okay, so chapter 1 is not going to be in a midterm. But the point here that I want to make is this is a viscous flow, and it can be thought of as a highly viscous fluid that is falling under the action of gravity. And you can apply your normal analysis, static analysis to this particular case and get an estimate. And people have done that. And the estimate of this viscosity comes out to be of the order of 10 to the power 8 pascals second. Okay. Do you remember what your viscosity for water approximately is? It's actually here, and it's written here itself. It's 10 to the power minus 3 pascals second is the viscosity of water at 20 degrees Celsius. So this viscosity of this fluid, pitch, is 11 orders of magnitude higher. So does our pitch qualify as a fluid or not? What do you think? So that's why I had said that if you do not discuss who the observer is who's asking this question and what kind of a watch the observer has, there is not much of a meaning in this particular question. So the question has to be well posed. Okay. So again, as I said, this is just a beautiful, if you want, it's a very short manuscript. It's just about 3 pages, I think. And I encourage you to go ahead and read this. And okay, so I'll just go back to the discussion here. So you can now understand that the T observation is very important. Right? This is the time scale of the observer. It's extremely important to discuss the question of what is a fluid. Okay. Now I'd like to take you to another historical detour of this is a very famous paper. It's a 1-page paper actually, that's it. And it defines a non-dimensional number. Remember in the last lecture I was telling you the last part, the beginning part of this first lecture, I was telling you that there are these different non-dimensional numbers. Some non-dimensional numbers are ratios of forces, some are ratios of time scales, some are ratios of length scales, some are ratios of velocities. And we saw the Knudsen number, which is a ratio of time scale, length scales, apologies. And here we have a number that we are going to see, the Deborah number. Here it is, they use the symbol D, but typically nowadays they use the symbol DE for Deborah number. I'll come to the definition of it in a second. So I'm just going, this is a very interesting paper again, and if you want you can read it. It was published in 1964 in Physics Today, and this guy, Renner, he's discussing his trip to and he's discussing. So when he arrived, he's talking to Bingham. And by the way, there's a very famous material called the Bingham plastic. So he's discussing, all these questions were being discussed about fluids and how do different materials behave, and the realization that there are different types of materials. And he brings out the important or the topic of what flows. And here he's referring to, this is so this is the highlighted part here, right here, which I'll read out. He's relating it to his discussing a passage from the Old Testament, where there's a prophetess Deborah, and in her famous song about the victory over the Philistines, she sang, "The mountains flowed before the Lord." When over 300 years ago the Bible was translated in English, the translators who had never heard of Heraclitus translated the passage as, "The mountains melted before the Lord." And so it stands in the authorized version. But Deborah knew two things. First, that mountains flow as everything flows. Okay? Everything flows. Because it depends on who is observing. If you have the right observer, even the mountains will flow. And then he goes on to define this Deborah number, which is given as time of relaxation by time of observation. Okay, and this becomes a very, very important Deborah number. Very, very important non-dimensional number in our particular case. Okay, so you can read the rest of it again. As I said, it's these should be very easily available to almost all of you if you do a quick Google search. So okay, I'm sorry, this has not come out very well for some reason. Okay, so I'll just go back to this document and I'll start writing it here. So Deborah number DE is wait, I'll just use another color. Black is a better color, it just looks. So Deborah number is given as time of relaxation by time of observation. So lambda by T observation. Okay, but what is this lambda? So this, it says it's the time of relaxation. Now this time of relaxation is a very simple idea, and let me see if I